Good morning. Thank you, Jan Dirk, for that very nice introduction. I hope I can live up to it. It's a little overwhelming. I also would like to thank Ellen and David for inviting me to give a plenary lecture. I really feel honored to be part of this really wonderful ICC. So I'm going to talk about high-temperature electrocatalysis, but focusing mostly on solid oxide electrolyte cells. So these are electrolytic cells that operate at temperatures above 400 degrees centigrade. It may be as high as 800 or 1,000 degrees C. They have dense solid electrodes. These are usually mixed ionic electronic conductors. Ion conduction takes place through a dense solid electrolyte, and the best known example of high temperature electrocatalysis is, of course, solid oxide fuel cells. Now, there are many advantages to high temperature electrocatalysis. High temperature improves kinetics, ionic conductivity, and electronic conductivity usually increase with increasing temperature. There's a large array of materials, ceramic materials, that can be used as electrodes, such as perovskite oxides or double perovskites. These materials don't rely on precious metals, and it's possible to fine-tune the properties of these materials by doping either the A site or the B site, or both, with various elements, and possibilities are almost endless. Of course, there are challenges. The electrolyte needs to be in perfect contact with the anode and the cathode. The thermal expansion coefficients need to match really well. Cell fabrication and sealing issues are not trivial. They may be costly and difficult. And operando characterization of the catalytic phenomena is really difficult. Solid oxide electrolyte cells can operate in three modes: as a solid oxide fuel cell, where we generate power, in the electrolysis mode, or in an ion pump mode. And I will give examples from our research for all three modes. So the first example from our labs is high temperature carbon dioxide and water reduction, or co-reduction. Of course, there's a lot of work going on looking at the low temperature CO2 electrolysis. In this case, it is happening in aqueous medium, temperatures less than 100 degrees centigrade. Products are usually C1 hydrocarbons. For the high temperature case, we are operating at temperatures above 500 degrees C, and if it is done together with water electrolysis, the products are CO and hydrogen, which is syngas. If we look at the energy requirement and see how that's changing with temperature, the total energy requirement is about the same. Maybe it's a little higher with temperature. But if we look at delta G, which really represents the electricity that's needed, what we see here is that it goes down with temperature. And since electricity is the most versatile form of energy, it is a major advantage. Now, in the CO2 and water electrolysis in an SOEC, the reactions that's happening on the cathode are CO2 and water reduction, releasing oxide ions. Oxide ions are transported through the electrolyte to the anode. On the anode, we have the oxygen evolution reaction and end up with pure oxygen as a byproduct. Now, the cathodes should have obviously high electrical and ionic conductivity, high thermal stability, and also suitable thermal expansion coefficients. The materials that we have been working with are perovskite oxides. They have formulas of AbO3. A is an alkali or alkaline metal, and B is usually a transition metal. Now, it's possible to do the tuning, for example, by introducing oxygen vacancies. We can increase the oxygen ion mobility. And by changing the B site doping and increasing the redox couple, we can increase the transportation of electrons. The material that I will talk about this morning is a lanthanum strontium iron oxide. And we're using an EDTA citric acid complexation method to synthesize them. It's a sol-gel technique. And we first looked at the effect of A-site stoichiometry. So we prepared samples where A-site is stoichiometric, or it has excess ions, or it is A-site deficient. Now, if we look at how the A-site stoichiometry is impacting, we're looking at the iron KH using EXAFS technique. And what we see here is as the A-site stoichiometry is decreasing, as we go from excess to deficient samples, the coordination number is decreasing. And that really implies that we are creating more oxygen vacancies, and it will help with the higher ionic conductivity. If we look at the iron oxidation state, what we see here is it's increasing as we go from excess to deficient samples, and it really will help with the higher electronic conductivity. Now, when we did the measurements, it is indeed the case, and we see that the A-site deficiency gives the highest electronic conductivity, as you see here, and it also has the highest oxygen vacancy formation and highest oxide ion mobility. If we look at how the A-site occupancy is affecting the electrocatalytic activity, what we see here is this is for the CO2 conversion, and we are operating at 800 degrees centigrade. The highest Faradaic efficiency is also achieved with A-site deficient samples. And Faradaic efficiency is really a measure of how well we are utilizing the electrons that we are providing. So in this case, 100% Faradaic efficiency means that almost 100% of the electrons are used for making the product that we are interested in. If you look at the current voltage relationship, the lowest voltage for any current is, again, for the A-site deficient sample. And again, it is a good thing because the lower voltage means lower electricity consumption. Now we're moving on to B-site doping. We're keeping the A-site stoichiometry at the deficient levels, and we're doping the B-site with nickel or cobalt, in some cases with one or the other, or sometimes with both. So how does doping the B-site affect the structural and chemical properties? I will not go through the details of the characterization results, but I will just show some of the what we found out. So using in situ X-ray diffraction technique, what we see is that structural integrity is not affected by B-site doping. Temperature program oxygen evolution technique shows us that we have more oxygen vacancies. XPS and Zane's data show that the oxidation state of iron has increased. The conductivity measurements taken at different atmospheres, different temperatures show electronic conductivity has also increased with B-site doping. So to summarize, nickel and cobalt doping is improving the electrochemical properties. Something in my eye. If we look at the electrocatalytic co-reduction activity, we see that the effect is in different directions. So increasing the nickel doping is increasing the water electrolysis activity, as we see here. Increasing the cobalt doping is increasing the CO2 electrolysis activity. So why are these different? Why are these in opposite direction? Maybe one of the first clues come from looking at the in situ drifts data when we have CO2 and water adsorbed at 450 degrees centigrade, and then we're looking at the desorption data using drifts at a constant temperature, looking at it as a function of time. And what we see here is CO2 is interacting much more strongly for the sample which has been doped with cobalt compared to the one which is doped with nickel. Is co-doping important? And the answer is yes. And the best CO production rate, for example, is achieved when we have both nickel and cobalt doping. Also, the best Faradaic efficiencies are obtained with the co-doped samples. So what is changing during electrocatalysis? And this is one of the challenges, looking at these interfaces or surfaces under electrocatalytic reaction conditions. So for this, we designed an operando Zane cell where we are using a fluorescence detector, and we are essentially recreating the conditions for the electrocatalytic cell. And the X-ray beams is at a 45-degree angle to the surface of the, in this case, the cathode. And we're, again, working with 800 degrees centigrade. The composition is identical to what we have in a typical electrolytic cell. And we have conducted these experiments at the Advanced Photon Source of the Argonne National Lab. So if we look at the iron K edge for nickel dope sample or cobalt dope sample, we don't really see much of a change in the iron K edge. So there isn't really that much of an effect. These graphs look crowded because we have the references, iron foil and iron oxide, but we're really looking at it at OCV, room temperature, OCV, this is open circuit voltage, 800 degrees C, and then when we are applying a bias. When we look at the nickel K edge, again, we don't really see much of a change. But if we look at the cobalt edge, we see that there is a difference. There is something changing with temperature or application of a bias. If we look at that region a little more closely, what we see here is that cobalt is first getting reduced when we heat it, and then it is getting reoxidized during electrolysis, thus decreasing the oxygen vacancy. But if we repeat this experiment with a co-dope sample, we see that cobalt is not really changing during electrolysis, so the presence of nickel is really keeping cobalt at a more stable state. Now, it is also possible to use the perovskite composition to change the hydrogen to CO ratio. And in this case, for example, depending on the composition, we can go hydrogen to CO ratios much less than 1, all the way to as high as 4. So that means without doing any detailed separations, we can really control the syngas composition by changing the composition of the perovskite. Now I'm going to move on to a concept of exsolution of active phases to the electrode surface. Now, exsolution is not a new phenomenon. It has been reported in the literature for some time, and it is really in a reducing environment and at suitable temperatures, B-site metals from the perovskite lattice really move to the surface. It's a migration, and exsolution leads to more oxygen vacancies. It creates metallic nanoparticles on the surface. Sometimes they may also be alloys. And then there are structural changes on the surface. If we compare, for example, nickel particles or cobalt particles on the surface through the exsolution process, as opposed to one that we may have put them on using like an impregnation method, these are really firmly anchored through this exsolution process, whereas if it is deposited, the interaction is much weaker. So actually, these environmental TEM images were taken right here in Lyon at the IRC Environmental. And we are looking at these surfaces. This is a sample which has nickel in the B site. And we are using 1 millibar of hydrogen. And we first see the onset of evolution of exsolution at temperatures as low as 400 degrees centigrade. And then nanoparticles continue forming, and the particle size is about constant. And after maybe 750 degrees centigrade, there is some growth in the particle size. Now, another observation we made was that there is some change where this exsolution is taking place. So where the socket is happening, it is changing from an orthorhombic structure to a tetragonal perovskite structure. And we have also seen that exsolution process can be reversible, but I won't talk about it at this talk. So it is possible to exsolve metal or alloy particles at high temperatures in a reducing environment, or in situ during a reaction. We have later seen that during oxidative coupling of methane, but the process takes time. An alternative is electrochemical exsolution. What we have found out is that by applying a cathodic potential, within minutes, like less than a minute, we start having exsolution of metallic particles to the surface. In this case, again, we're looking at lanthanum, strontium, cobalt ferrite, and within 2 minutes, the surface is fully decorated, and you can actually see here the metal particle, and if you look at the cobalt, it's a little harder to see, but there is some of the X-ray mapping showing the cobalt on the exsoluted particle. Now, we were able to observe this phenomenon in situ using an NAP-XPS technique at the Brookhaven National Lab. So if we look at the iron 2p region, there is the iron 0 formation. So there is metallic iron formation, but it takes longer and it is not as prominent. But if you look at the cobalt, it is essentially going from a +2 oxidation state to mostly a 0 oxidation state within 1 minute. So the exsolution is happening, and we can observe it in situ using this NAP-XPS technique. Now, we have also looked at the same phenomenon using the NEXAFs, again at Brookhaven National Lab, and the iron LH did not really show much change as we went from OCV to a cathodic current application or voltage application. But if we look at the cobalt LH, we clearly see that there is a significant reduction of the cobalt. So actually, this data support our hypothesis that exsolution under a cathodic bias is happening. So what are the implications of exsolution for catalytic activity? Well, if we look at how CO2 adsorption is changing, again, we're comparing the parent perovskite, in this case LSNF, and the X-salt one. The CO2 adsorption is much stronger. And this is happening at 450 degrees C. So we're clearly changing the adsorption characteristics. If we look at the electrocatalytic activity for CO2 reduction, CO production rate is much higher for the X-salt sample. And also Faraday efficiency is much higher. It is really right around 100% for the X-salt particle, samples. So X solution is improving the catalytic activity and Faraday efficiency. If we look at how the potential is changing for water electrolysis, CO2 electrolysis, or co-electrolysis of water and CO2, again, in each case, the sample which has gone through the reduction is giving us a lower voltage, which is good. That means less electricity for the electrolysis. And if we look at the impedance data, electrochemical impedance is lower for the sample that has gone through the X solution. And for those of you who are not familiar with the impedance, the radius of the arc really represents the resistance of the impedance, and the smaller it is, the less resistance we have, and this is what's happening in this case. And one final slide on the CO2 case, and when we kept this cell online for 100 hours, it was very stable. You can see the cell voltage here, Faraday efficiency right around 100%. And then we also looked at post-mortem characterization, and the sample really did not show any coking on the surface. We didn't really see the D or G bands. So there's very good stability. Now I'm going to shift gears and move on to another example from our labs, again in electrolysis mode. This time we're looking at high temperature ammonia production from nitrogen and water. Now, obviously, ammonia is a very important chemical. It's used for making fertilizers. Most of ammonia production of the world, more than 85%, is used for ammonia production. And if you look at world population increase versus fertilizer use, there is a very nice correlation. It's almost 1-to-1. The more the world population increases, the more fertilizer use we're going to need. Of course, there's a commercial process, Haber-Bosch process, which has been around more than 100 years. It's a well-known process. It works. There are many advantages, well-known catalytic system. The disadvantages are it's very energy intensive. Hydrogen that's used for the Haber-Bosch process is really, it comes from methane. And for every kilogram of ammonia we produce, we're emitting 2.5 kilograms of CO2. And if you consider how much ammonia we're making, you can do the math. So it's very fossil fuel dependent. It requires high temperatures and pressures. And because of the high pressures and temperatures, materials are more expensive and there are safety issues. Now, electrocatalytic ammonia production may allow small-scale modular production. It may allow production at the point of need, so you don't have to transport ammonia from one place to another. For example, you can make ammonia in modular form at where we have the fertilizer plant or close to the agricultural site. So we are, again, using a solid oxide electrolytic cell for this. The cathode really has to have a multifunctional performance. So what we are expecting the cathode to do is both water electrolysis, water reduction, but also nitrogen activation, nitrogen reduction. So it is a lot to ask for a cathode. So first we thought, well, how about if we introduce a composite cathode concept? So rather than trying to find just one material which will do both, we're going to have both a perovskite and a nitride phase. Perovskite oxide will do the water electrolysis, and the nitride phase will promote the nitrogen activation and provide the nitride ion mobility. So first, for the perovskite phase, we're using something that we're quite familiar with, lanthanum strontium nickel ferrite. And we are looking at water reduction. The left side shows that we are producing hydrogen quite readily. This is as a functional current density, and the water dissociation also takes place. So even without electrocatalytic activity, we can get water dissociation. Now, we have to take an iron oxide phase and convert it into an iron nitride, or at least iron oxynitride, using an ammonia treatment. So we're starting with Fe2O3, and depending on the temperature and the duration of nitridation, we start seeing the iron nitride phase. So at 450 degrees centigrade, most of what we have is Fe3N phase, which dominates the structure. If we go to higher temperatures, like 500 degrees centigrade, we start seeing a gamma Fe4N phase, and that's a nitrogen deficient sample, and that's not what we want. So we probably want to stay at nitridation temperatures below 500 degrees C. We have also looked at the Mossbauer data. Again, this was performed here in Lyon in collaboration with my good friend and collaborator, Jean-Marc Millet, at the IRCE Lyon. So we, again, see at 400 degrees centigrade, there are two sextets, and as temperature increases, we're beginning to see Fe3N formation, and also at higher temperatures, Fe4N formation, as you can see here. So we clearly have an oxynitride phase. Now, another characterization we've done on these materials was an argon ion etching, looking at the nitrogen 1s region, argon ion etching, to look at how the surface is different from the bulk. And we looked at the three samples which were nitrided at three different temperatures, 400, 450, and 500 degrees centigrade. And what we're seeing is, as we increase the etching time, as we go up in this direction, the amount of iron oxynitride is decreasing, and iron nitride is increasing. So this suggests a model where there is an iron nitride core surrounded by an iron oxynitride shell. Now, we wanted to see if the nitrogen in these materials are accessible. So we did some temperature program desorption, or you can also call it decomposition, because at higher temperatures. So nitrogen is evolving. Again, it depends on the temperature of nitriding. But the one that was nitrided at 450 degrees centigrade has the highest amount of accessible nitrogen in its lattice structure. We also did temperature program reaction with water, and you can see that with water, we are making ammonia. So the nitrogen in the lattice is accessible. Now, if we look at the electrocatalytic ammonia synthesis on this composite cathode, which is a mixture, a physical mixture of LSNF and Fe3N, iron oxynitride, we see that we are making ammonia. At higher current values, the electrolysis of water really takes over, so there's some decline after that, but we're clearly making ammonia. And compared to the blue bars, which are almost negligible, we have made a 2 orders of magnitude improvement in the ammonia production rate. Okay, that's all good and fine, but putting two phases physically together and hoping that they will be in intimate contact is a lot to ask for. So we came up with the question, well, can we come up with a single phase where we can combine both functionalities in a single material? So we went to a double perovskite structure, in this case, strontium iron molybdenum oxide. And we, again, synthesized them using a sol-gel technique similar to other perovskite structures we have made. And we looked at their stability, structural stability, using in situ XRD. And what we see here is up to a 700 degrees centigrade. It's quite stable, so we don't really change anything in the crystalline structure. And then now we're nitriding it using ammonia at 2 different temperatures, and we clearly see that we are beginning to form an oxynitride or nitride phase. Now, again, if we look at the nitrogen accessibility using temperature program desorption technique, nitrogen is quite readily accessible. It evolves from the lattice, and also it can react. In this case, we tried it with hydrogen. It can react with hydrogen in the gas phase and form ammonia. Now, if we look at the electrocatalytic ammonia synthesis activity, what we see here is this is just the oxide phase, strontium, iron, molybdenum oxide, and this is the nitrided form. So we have improved the activity 10 times. A very important control experiment we did was by replacing the gas phase nitrogen with argon. Why was it important? Because we wanted to make sure that the ammonia we're making is not simply using the nitrogen from the lattice, but it is indeed activating nitrogen from the gas phase. So by replacing argon, the ammonia synthesis rate really went down, so we're clearly activating nitrogen from the gas phase. So what's happening here is lattice nitrogen is being used and creating nitrogen vacancies, and then the nitrogen in the gas phase is filling the nitrogen, and the cycle is completing. And this is really a Mars-Van Crevelen type mechanism. That's what we are suspecting. One final comparison is if we look at this nitrided double perovskite sample versus the composite cathode, where we put a perovskite and a metal nitride together, we have a better ammonia production rate. So this oxynitride composite cathode, although it worked, the single phase is working better. Now, what's happening on the cathode surface during high temperature electrocatalytic production of ammonia? Again, this requires some synchrotron techniques. And again, we were using the synchrotron facilities at the Argonne National Lab. And here we have designed a cell where we're changing the incident angle of the operando X-ray absorption cell. So by making the incident angle much smaller, you can make the technique more and more surface sensitive. So here, first of all, we're looking at the oxidation state of iron, and it is at a state higher than +3. So there is really this Fe+4, Fe+3 redox couples. That's what we learned from here. And if we look at the effect of incident angle, there isn't really much change when we're looking at the iron signal, and not much change whether we're looking at the bulk or the surface. And also oxidation state of iron, whether we're heating it or applying a potential, is not really changing much. Then we looked at strontium KH, and this first line shows the 45-degree incident angle. And as you can see, whether we're operating at 25 degrees C, zero current, high temperature, or with application of some current, it's pretty much constant. But if we change the incident angle to 2 degrees and make it much more surface sensitive, then we start seeing changes. So what's happening here is strontium is first getting reduced when we heat it from room temperature to 600 degrees centigrade, and then at OCV, and then when we apply a current, it is getting reoxidized. So again, this may have very important implications for the catalytic or electrocatalytic activity. I'm going to switch gears again, and these two examples will be very short. Now, this time, we're looking at two oxidation reactions and looking at these electrolytic cells in ion pump mode. So the first example is oxidative dehydrogenation of lower alkanes. Now, I'm sure there are many of you who worked in oxidation realm, and especially in ODH. One of the main challenges is the selectivity, because when we have the gas phase in contact with the olefin being much more reactive than the alkane, it immediately or readily reacts further, oxidizes further to CO2 and water. So using an electrolytic cell is really preventing the olefin from ever being in contact with the gas phase, because on the cathode, we have the oxygen reduction reaction, and oxide ions are traveling through the electrolyte to the anode, and on the anode, we have the hydrocarbon oxidation, and the only thing is different oxygen species. So first of all, again, we have oxide ions, so the thermodynamic limitation is lifted, so we still have oxidative dehydrogenation. Any carbonaceous species which may be left behind also gets further oxidized, so coking problems are eliminated for the most part. And then we can really control the flux to the surface. And of course, we can change the catalytic properties of the anode surface, acidity, surface energetics, by tuning the material properties. So in this case, the material we chose was a strontium titanate, and we doped the A site with lanthanum, and then we replaced partially the oxygen ions with chlorine, and we have seen very different catalytic or electrocatalytic behavior. And the anode is where the oxidation is happening, and for cathode, we can really pick any material. So this is operating as an ion pump, and we wanted to see if we can really get an oxygen flux from the cathode to the anode. So this can also be looked at as air separation process. So here we have air, and we're at different current densities. We're looking at the oxygen flux, And the straight line represents what is theoretically possible using the Faraday's law. And we're very close to the straight line. At higher current densities, there's some deviation, because we later found out that there was some reduction of the perovskite, but once it reaches a steady state, it is very constant. And rather than showing all the electrocatalytic data, I thought I would just show a comparison of catalytic or thermal catalytic versus electrocatalytic ODH. And we're looking at these selectivities at an equal conversion level, and we picked a 15% conversion level. So the blue bars are the pack bed, and the red ones are electrocatalytic. Clearly, ethylene selectivity is much higher for the electrocatalytic case, and the COX selectivity is much lower, again, for the electrocatalytic case. So clearly, we can really control the selectivity much better if we are using an electrocatalytic operation. Another example, and I promise this is the last example, is electrocatalytically assisted oxidative coupling of methane. And in this case, we were using a lanthanum strontium cobalt ferrite perovskite. And one thing we have observed, and first it was surprising to us, if we kept the cell online for some time, within a matter of hours, the C2 selectivity kept improving. It went from about maybe 20% to 50, 55%. And then the CO2 selectivity kept coming down. And we said, okay, something is clearly changing, and what is changing? So we have done some post-mortem characterization, and what we have seen was that the cobalt particles had really exuded to the surface, and we had some metal particles, nanoparticles on the surface. And this was done at 850 degrees centigrade. Now, if we look at the long-term stability, and we kept it online for 100 hours, and what we have seen is this is the potential. It's very constant. This is Faraday's efficiency, right around 100%. And this is C2 plus selectivity. We were also getting some C3 components in the product stream. And production rate is also very, very constant for 100 hours. So these are all the examples. So I hope I was able to convey the message that high-temperature electrocatalysis really offers a lot of advantages and many opportunities for applications ranging from energy, environmental protection, or chemical manufacturing. There are, of course, many challenges remaining, and most important challenges, in addition to manufacturing the cell, those can be handled. But the difficulty of characterizing the electrocatalytic phenomena under reaction conditions at high temperatures under an electrical bias, which require developing new tools and new techniques. I'd like to acknowledge a large number of collaborators who contributed to different parts of these many projects that I talked about. And as you can see, some collaborators from France, some from South Korea, several from the US, many national laboratories, including Argonne National Lab, Oak Ridge, Brookhaven, SLAC, which we are starting with a new collaboration very soon, and some of my own colleagues at Ohio State and, of course, Purdue University. These are people who worked on these projects. Many of them are graduated. They're doing really well. Some of them are current students or postdocs. There are also some undergraduates among them. And then I'd like to finish by acknowledging the financial support that provided support for these projects. US Department of Energy, US National Science Foundation, my research group. Again, I spent some sabbatical time at Lyon. and developed some very productive collaborations. I'm very grateful for that. National labs, especially Argonne, Brookhaven, and Oak Ridge. And again, I'd like to thank you for your attention, and I'd like to thank the organizers for putting together such a wonderful ICC. Since I was part of the ICC previous one, which never happened, I know how much work goes into it. So my hat is off to you. It is a really, really great meeting. Thank you very much.